Kurchatov Institute, the analog of Los Alamos, Russian analog of Los Alamos nuclear weapon lab. And so he was a student of Yuri Kagan and Smaradinsky, and so both are disciples of Landau. And so which makes Zhora, like Boris Swistunov, Zhora is second generation Landau school. So then now Zhora is professor simultaneously in Amsterdam and Paris since 2003. I think everyone of us know his contributions. Thank you very much for coming.
Thank you, Yegor. First of all, I'm grateful to the organizers for inviting me here to Stockholm. I have been here 15 years ago. It's always nice to come back after a long time. And so what I will do, I will talk about ultra-cold molecules and dipole systems. And before I do that, because there is new physics coming out and there is a search for novel phases, and I will try to explain why this domain is interesting. But before that, I actually have a question to the audience. Yes. I see that there are people here. I see clearly 1, 2, 3, etc. Yes, particular scientific people who are very much familiar with what is happening in ultra-cold quantum gas, what experiments are about, and so on. There are even people who wrote books on this subject. Yes, and but at the same time, I see people who come from condensed matter physics and that do completely different things. And therefore, what I would like to ask you is, do I have to give a brief historical introduction of what was happening with atomic fermions in the last, let's say, 7, 10 years, or you are assumed to know everything about them? How do you think?
You have a carte blanche. So,
no, but I'm just asking the audience.
I think an introduction would be good.
Okay. So then, what I will first do, I have a few slides regarding that. I will tell you about atomic fermions and BCS-BEC crossovers from the interacting regime, molecular BCP wave resonance for atomic fermions. And then it will become clear why ultra-cold polar molecules became so interesting. Actually, until very recently, all experiments with atomic fermions have been done with two-component gases of potassium-40 or two-component gases of lithium-6. What do I mean by saying two-component? It means that people store in an optical trap or magnetic trap or magneto-optical trap two internal states of potassium-40 or two internal states of lithium-6. In this respect, the system is equivalent to the so-called spin-1/2 fermions, electron spin up, electron spin down. Yes, and the difference is that in the case of atomic gases, spin up is one internal state, hyperfine state, and spin down is the other hyperfine state. So then, we are considering the so-called ultra-cold limit, where the thermal de Broglie wavelength of particles is much larger than the characteristic radius of interaction between them. And dilute limit, where the mean interparticle distance is much larger than the characteristic radius of interaction between particles. This characteristic radius of interaction between particles is here R. So, the system is dilute, and at the same time, only the S-wave scattering is usually important because the thermal de Broglie wavelength greatly exceeds the characteristic radius of the interaction potential. So if I have two different internal states of one and the same atom, only different internal states interact with each other because identical fermions in one and the same quantum state do not undergo S-wave scattering. So it's a clear analog of spin-1/2 fermions. Yes. Then, in such a system, already 12 years ago, people have reached the regime of quantum degeneracy, and the distribution of the Fermi C, and this has been done in the lab of David Jean at GR with potassium-4. And then, so just for your information, that at present, people who are working with these systems are dealing with densities 10 to the 13th, 10 to the 14th particles per cubic centimeters and temperatures, let's say from 1 microkelvin to 100 nanokelvins, slightly lower. Just for your information, until recently, the world record in cooling ultra-cold atoms was belonging to Wolfgang Ketterle, and it was equal to 450 picokelvin for bosons, which are easier to cool. And recently, Wolfgang was giving a talk in the Zush, and he announced his new record, 350 picokelvin. And they intend to go down to 50 picokelvin. Yes, they needed to know this. Yes.
How did he measure such low temperature reliably?
Because what they do, they first, in the first experiment, what they have done, this was a few years ago, they have created a Bose-Einstein condensate at this density, yes, and then they adiabatically expanded the trap, yes, and compensating the gravity and so on. And then what happens is that initially there was a certain very, very minute thermal cloud, and then it remained the same because, you know, the density was going down to 10 to 11, yes. Therefore, when I'm talking about these temperatures, 450 picokelvin in the first experiment, it was a very low density, which is equivalent to having, let's say, higher density and temperatures of, let's say, 50 nanokelvin or something, yes. Because when you expand, you decrease the density, and then it's easier to measure the thermal cloud, yes. And the present experiments where they reach lower temperatures are done in a lattice for, I think it's done for two-component bosons and so on. What, I did not exactly understand how they did this measurement, but the idea is to first cool the spin degrees of freedom, yes, and then transfer the very cold spin temperature to the translational motion, yes. And that's what Wolfgang was advertising, yes. But this is very, very easy, yes. So, then, you know, when people reach quantum degeneracy at these densities and these temperatures, there was a question of what to do next. And certainly, everybody is aware that what we are interested in is, for example, for fermions, to obtain a superfluid. Sorry? Oh. Sorry. I have to touch this computer. Yes. To reach the superfluid Bardeen-Cooper-Schiffer transition, where the transition temperature in the case of neutral atoms is exponentially small. If you read textbooks, you find this formula. Yes. So when fermions with momentum k and minus k on the Fermi surface form strongly correlated Cooper pairs, the transition temperature is that low, where k Fermi A is Fermi momentum multiplied with scattering amplitude, and this guy is much smaller than 1 with the interacting regime. Yes. And then what happens is that for realistic parameters, this A, which people have in experiments, this guy is fairly small, and the temperature is something like nanokelvin or lower, so cold. And people made these estimates, they started to speculate, what do we do, and so on. And then, what saved the situation are the so-called Fano-Feshbach resonances, which are in the physics of atomic gases are usually called just Feshbach resonances. This is the dependence of the scattering amplitude or scattering length on the magnetic field. For example, this is a typical picture for lithium. In here, the scattering length is small and negative. This corresponds to the BCS regime. Then it becomes negative and very large, and then the perturbative approaches, Migdal-Galitsky, Gorkov, Bardeen-Cooper-Schiffer, doesn't work here. Then it becomes positive and very large. None of the perturbative approaches here, it's a strongly interacting regime which resembles the situation in neutron matter, neutron stars. And here, the scattering length is positive and large, and one expects the behavior of a Fermi liquid, because it's just a Fermi gas with repulsive interaction between particles. But this is not what is happening, because when the scattering length is positive and large, two fermions spin up and spin down, let's say two different internal states, they form weakly bound molecular states with the binding energy which is inversely proportional to the scattering length in the square, and that's what is happening in real life. They form weakly bound dimers or molecules. These are composite bosons which are supposed to undergo boson-Einstein condensation. Does everyone understand why the formation of molecules is happening here? It's a very interesting problem which is nicely explained in textbooks, yes, but I would like to give you a physical information. Three-dimensional case. Imagine, please, that there is an interaction potential which is a potential wave. And there are very many bound states. Yes? And there is an incident particle with an energy tending to zero, outer pole. Question. Does this potential well reflect or attract this particle? And the answer is, it can be both. Everything depends on the position of the last state, or the last bound state. If this state is really weakly bound, very close to the continuum, then the interaction amplitude is positive, which means strong repulsion. Yes, and this is typical for the three-dimensional case. Yes, and so it's more or less counterintuitive. Two particles can form a weakly bound state, but at the same time, the interaction amplitude in the continuum spectrum corresponds to a very strong repulsion. That's what is the case here. And so that's what the situation is. I should probably explain to people from other fields why this strange dependence on the magnetic field happens. And this is because, imagine please that you have two atoms. Very simple problem. This is the interaction potential. Think of it as Leonard Jones. There is a van der Waals tail, there is a potential well and repulsive core. Then, two atoms in different internal states, for example, this blue and green means two different internal states, spin up and spin down, fermions. They approach each other. The hyperfine interaction between these guys, it may induce a virtual transition to different internal states. The change of an internal state, of a hyperfine state of one or of both atoms, means that from this potential curve, I go to another one which is shifted by the so-called hyperfine energy, the difference in the energy of internal states. Then, if the continuum of states in this green potential curve almost coincides with a bound state in this brown curve, then there is a resonance. As we understand from theoretical physics, this is the Breit-Wigner problem, yes? And then the scattering amplitude, as we know, undergoes resonance, and this is exactly this behavior which is shown here. This resonance, where the scattering amplitude is infinite, almost infinite, it just corresponds to the case where the continuum of states along this potential curve coincides with the bound state of this guy. And this problem has been introduced in theoretical physics to Breit and Wigner in 1930 and something. And then, somewhat later, in 50s, two people, Ugo Fano and Ferschbach, they thoroughly investigated this problem. It was called bound level on the background of the continuum. Yes, and Ugo Fano did it in relation to atomic and condensed matter physics, and Ferschbach did it in relation to nuclear physics. None of them refers to each other, and none of them refers to Breit and Wigner. Yes, so this happens. Yes, but the physics is there, and then what happened is that these Ferschbach resonances, they have been introduced into physics of quantum gases by Baudouin Ferhard in 1993, and Baudouin has his education in nuclear physics. Therefore, we got the term flashback resonance. In a later stage, when many atomic physicists started to work on the subject, and many people from condensed matter came, they said, why just flashback? It should be fun of flashback. Now, many people call it fun of flashback resonance. Yes, that's what it is. Now, so we have this picture, yes. So we have a regime of BCS where the scattering amplitude is negative and small. BCS transition temperature is extremely low. We have strongly interacting regime, which no one knows what is happening there, unless there are Monte Carlo people who do thorough calculations. And we have the regime of composite bosons formed by spin-up and spin-down fermions. Then what happened in a later stage is that, so we have these regimes, yes, and then people started to speculate what is happening, what is the superfluid transition temperature. It immediately became clear that there is an analog of this phenomenon in the physics of superconductivity, and there is a nice work of Tony Leggett from 1980 or 81, I forgot, where he described this crossover from BCS to BEC. And Nozier and Schmittring did it at a finite temperature. And there was a related work for two-dimensional helium field, where a similar phenomenon is happening. So, I would like to make two comments. Here is just a sketch of superfluid transition temperature in terms of a Fermi energy for atoms. It's very low, exponentially small in the BCS regime. It is something in the strongly interacting regime. If Swisnov were here, he would immediately say that I should just draw here as a solid curve, because the Monte Carlo calculation just gives a very solid result. Yes. But I would say that several Monte Carlo calculations are slightly different from each other. Yes. They are more or less about the same, but there is a certain discrepancy. And here I have a molecular BEC of composite bosons, yes, and then the transition temperature is just the Bose-Einstein to condensation temperature for a weakly interacting boson gas. Yes. So this is the picture, and actually this type of picture was already present some time ago in Nozier and Schmittring. Yes. What cold atoms do, they provide us with the possibility to know the exact picture, how the transition temperature goes, how to calculate, and so on. And there is one more question. There is a common belief that when I go from this regime, from the regime of BCS to the strongly interacting regime and then to these molecules and molecular BEC, it's a crossover if the interaction is S-wave. It's not a quantum transition. Yes, at zero temperature. And the reason why people believe that is that the symmetry of the BCS wave function and the symmetry of the condensate wave function of the molecules is the same, it doesn't change. Although, I would like to say that, for example, several reasonable people were arguing not a very long time ago that it's not completely clear whether this is a crossover. There is no rigorous proof. Yes, do not request a rigorous proof. Yes, okay. Now, let me say that, you know, this strongly interacting regime where the scattering amplitude is infinite or close to infinity attracted a lot of attention. Very many people from high energy and nuclear physics came because it has an analogy with nuclear physics. And then, what is happening here? Imagine that the scattering amplitude is tending to infinity. What matters in all equations is not the scattering length itself, but unit divided by the scattering length, like in the Papapyrov boundary condition. Therefore, what happens is that this guy drops out of the answer, and there is only one distance scale in the problem, mean interparticle separation, density in the power of -1/3. There is only one energy scale, which is the Fermi energy density in the power of 2/3 divided by the mass, and there is universal thermodynamics. When I get a finite temperature, the energy scale temperature arrives at the game, and the length scale of the sum of the wavelength. Very nice universal thermodynamics described by Jason Hall. Then, there were very many people writing down set of diagrams in this strongly interacting regime. Yes? But the problem is that there is no small parameter in this case. And therefore, if you cut your diagram somewhere and say, okay, let me throw away part of them and take into account this set of diagrams, it's not completely clear how good your answer is. This is what I'm usually saying to all these people. Yes, but okay. And there is a debate now. Well, maybe it's not that bad if I just take this set of diagrams. Maybe, but who knows? But what is reliable here are Monte Carlo studies. Yes, and they have calculated that the chemical potential is approximately 0.4 of the Fermi energy. For an ideal gas, will be just 1 here. Yes, and then there were very many people obtaining this number. Then what people have done, they have calculated the transition temperature, for example, at unitarity. The unitarity is called the case where A is tending to infinity. It turns out to be 0.15 or 0.16 of the Fermi energy. There are very extensive calculations by Tristonov, Prokofiev, and Matthias Troyer. Yes, and they have also calculated how the transition temperature behaves itself as a function of this scale. And there were very many experiments where people were trying to measure the gap in the energy spectrum. Then they were trying to measure damping of excitations, measuring heat capacity, study thermodynamics, and so on. Very extensive studies have been made. I would like to mention only one thing. This is the question how to identify that the system is superfluid. And this is Wolfgang Ketterle, who first did this experiment. What he said is the following. Let me create a strongly interacting Fermi gas and rotate it. Yes. Then, if the system is superfluid, I am supposed to see the formation of vortices, quantum vortices, if the rotation frequency is sufficiently big. And that's what they saw experimentally. With a certain degree of imagination, you may say that these, you see here black dots, these are deep center density profile indicating that there is a vortex lattice. Yes, and that's what Wolfgang saw experimentally. So there is now a common belief that there is a direct proof of superfluidity. This was, I would say, the first remarkable result in these studies, achieving this strongly interacting regime, which brings in analogy with neutron matter. And there was another breakthrough in the field, which was also quite interesting. It was on the so-called positive side of the resonance, right here, where you have positive scattering length, and fermions, spin down and spin up fermions form weakly bound molecular states, composite bosons. What happens is the following, that in this case, when A becomes smaller than the mean interparticle distance, I have composite bosons. Their size is A, and it's much smaller than the distance between these composite bosons. I have Na cubed much smaller than 1 with interacting boson. So, there are now two questions. First of all, how these molecules interact with each other. Do they repel each other or do they attract each other? They are bosons, because if they attract each other, the Bose-Einstein condensate is attractive, it collapses. If they repel each other, it's okay. The second question is that I'm a little bit cheating you, because these weakly bound dimers are actually the highest possible raw vibrational state of the molecule. If I'm saying raw vibrational, it means rotational and vibrational, because the molecule undergoes vibrational motion and rotation. So this is the highest bound state. Then, it is supposed to undergo collisional relaxation. Two molecules collide. One of them goes to a deep bound state indicated here, and another one gets dissociated. It's a process of decay. It's very bad. The system decays. And then, for molecules consisting of bosonic atoms, such a process has been found to be very, very rapid, so that the characteristic lifetime of such a system would be of the order of milliseconds, which is not that much. So then, you know, Regarding the interaction between these molecules, there is a very old answer from condensed matter physics. And the answer is that, you know, two molecules, very long molecules, how do they interact with each other? Atom-atom scattering length is A. So this blue fermion interacts with this green fermion. This is 1A, and this blue interacts with this green fermion. This is another A. 1A plus 1A is 2A. 1 plus 1 equals to 2 was a very nice answer. Yes, of course, people were writing diagrams and doing calculations, but it was the answer in condensed matter physics. People studying BCS-BC crossover in the Leggett model. The Leggett model is a nice qualitative model, but it gives 2A. The true answer is 0.6A, yes, which means that the rate of elastic collisions is lower by an order of magnitude, which is not a big problem. It's only nice because there is an exact solution of the four-body problem, how two molecules interact with each other, and so on. But what is especially nice is that A is positive. Therefore, the molecule-molecule interaction is positive. And people arrived at the conclusion that the condensate of these molecules does not collapse. These composite bosons repel each other. What about this bad process of collisional relaxation? I just give you an idea of what was happening there and what was in a later stage important for pure. Imagine, please, that two molecules collide. Yes, this molecule collides with this one. The size of each molecule is of order A, which is big. But in order to undergo collisional relaxation, at least 3 of the 4 fermions have to approach each other at a short distance of the order of the size of the deep bound state, which is called here RE. And this RE is much smaller than A. We have a two-component system. If 3 particles approach each other, we have that 2 of them are green and 1 is blue, or 2 of them are blue and another one is green. Yes, and there is no other motion. Yes. So, therefore, what we should have a situation where 2 identical fermions should approach each other at a short distance of the order of RE. But we know from the Pauli principle that identical fermions do not like to approach each other. And their correlation function is their momentum multiplied the distance in the power of 2. I put here question mark because of the 3-body and 4-body dynamics. What is the characteristic momentum of fermions in the model? It's either the translational momentum, which is tending to 0, or the inverse size of the molecule. What is the inverse size of the molecule? It's unit divided by A, because the size is A. So therefore, I get RE divided by A in the power 2 with a question mark. This 2 with a question mark turns out to be 2.55. So therefore, if I restore dimensions, I see that this bad process of collisional relaxation, the probability, is proportional to RE divided by A in the power, this one, 2.5. And A is of the order of 1,000 angstroms, 2,000, 3,000 angstroms, and this guy is 50 angstroms for potassium and 20 for lithium. So I get a few orders of magnitude reduction. And this Pauli principle suppression of this bad process of collisional relaxation says that there is a remarkable collisional stability of those molecules. For example, look here. The probability of decay is inversely proportional to A in the power 2.5. What it means is that when I approach resonance, yes, I increase A, and the system becomes more and more stable. It's quite remarkable. You know, molecules, the atomic system, you make the binding energy smaller and smaller. The molecule becomes bigger and bigger, less and less bound. At the same time, the collisional stability becomes better and better. Absolutely counterintuitive and related to the fact that when you increase the size of the molecule, you decrease the effective momentum of fermions in the molecule. Therefore, the correlation function decreases. And that's what has been confirmed by experiments. I here make a comparison of theoretical predictions with experiment. And then, what people have done, they have done very nice experiments. This is a very dilute system, 10 to the 13, 10 to the 14th particle per cubic centimeter. There are 8, 9 orders of magnitude difference between this system and liquid helium-3. And it's much cooler. Here the temperature is 100 nanokelvin. In liquid helium it's millikelvin, tenth of a millikelvin. But then, you know, this system is quite nice. The rate of elastic collisions is big because the scattering amplitude is big, 0.68, A is big. And the relaxation, bad process, is suppressed. So if I make here the ratio of bad things to good things, yes, as usual in this life there are good things, elastic collision, evaporative cooling, and there are bad things, decay, yes. Then the ratio of bad to good is 10 to minus 4, which means that the system can be nicely evaporatively cooled and was condensed. And then all these laboratories have done that, and this was the first molecular Bose-Einstein condensate in the world. Yes. And this has been done starting from 2003. They have these experiments in 2004. It was already more or less set. Yes, with lithium and with potassium. But what is also nice, that these are the largest diatomic molecules obtained so far in the world. Before these experiments, the largest diatomic molecule was helium-2 molecule consisting of 2 helium atoms, ground state helium atoms, with the size of 100 angstroms and binding energy of 1.5 millikelvin. Here, the binding energy is much smaller. It can be tens of microkelvin or even microkelvin. And the size is 2,000 angstroms, even 3,000 angstroms, experimentally. Yes. The lifetime of these molecules with the collision and relaxation can be made on the order of minutes. So it's a very long time. And then, you know, people say that in principle one can increase this scattering length, the size of the molecule to 5,000 or even maybe 8 or 10,000. Just a little bit more, and this molecule, quantum object, can be visible by eye. It's a joke. But that's what people say. That's what the situation is. And then when you get this molecular Bose-Einstein condensate, you get typical pictures. For example, you have a trap, and this is your density distribution in the thermal regime. When you get the formation of a BEC, you get a sharp density peak in the center, because condensate has no temperature, and there is a balance in between repulsive interaction between particles and the confining potential, which leads to the formation of this density. Typical picture for the atoms, and now for the molecules. So there were two remarkable achievements in the studies of atomic fermions. The first one is the achievement of the strongly interacting regime and the proof of superfluidity. Yes. And second, the creation of these weakly bound, remarkably collisionally stable diatomic molecules via Bose-Einstein condensation, and the fact that they are the largest diatomic molecules in the world. Okay. And you know, what happened then is that people said to themselves, okay, we got nice physics, we did not reach the BCS regime, because being honest, I would like to say that if I return to my initial picture, which is right here, I would like to say that people reached this super strongly interacting regime. They reached the regime of these composite bosons. But they did not reach superfluidity here, because here the transition temperature is small. They more or less stopped their superfluid studies at K Fermi K 1 or 4.7 or something like that, just because of the very low value of the transition temperature. But then, another question which was there was the question, what if we try the P-wave Feshbach resonance? Just because we did nicely with the S-wave resonance, what happens if we deal with the P-wave resonance? And then, people did experiments, first at Gila, NS, then in Melbourne, Tokyo, and elsewhere. Then, I would like to say that in the 3D case, it should be power 3 here. But, you know, people understand that the P-wave interaction is usually very weak. So away from the P-wave resonance, the transition temperature is vanishingly low. In the exponent, I get unit divided by K Fermi multiplied atomic distance. In 2D, it's factor 2 here. In 3D, it's a U. It's practically 0. So I have to be very close to resonance in order to get a high transition temperature. The picture is more or less the same. BCS side, strongly interacting regime, and P-wave molecules. But it immediately became unclear that P-wave molecules are unstable, in contrast to the S-wave. The understanding is very simple. Imagine, please, that S-wave molecule, the orbital angular momentum is 0, so the effective potential is like that, and the wave function is more or less very, very long. P-wave molecules, there is a centrifugal barrier. And then, most of the wave function is sitting at inner distances. Yes. Therefore, the characteristic size of the molecule is fairly small, and the suppression of collision or relaxation due to the Pauli principle does not work. It works a little bit, but not much. Then, what happens in this strongly interacting regime? In the strongly interacting regime, what happens is that two atoms tunnel through the potential, through the centrifugal barrier, form a quasi-bound state which is fairly long-lived because the resonance is narrow. And this long-lived quasi-bound state of two atoms collide with a third atom, and the system undergoes collision or relaxation to these bound states. And there were several people investigating this phenomenon, and then, okay, so everybody confirms that here the system is collisionally unstable. Here it is very stable, but the superfluid transition temperature is vanishingly low. And then there were experiments, first at Gila at NS, then in Melbourne and Tokyo, which were saying that the lifetime of these P-wave molecules is of the order of tens of milliseconds. So the conclusion is that the system next to P-wave resonance has a problem because it is short-lived. What means short-lived? It means that if I create such a system, it gives 10 milliseconds, 20 milliseconds, 10 milliseconds. Okay. And this was very unfortunate because there were very interesting projects, the idea of which goes back to 1990s or 2000. Why is it actually so interesting to study P-wave resonances with atoms or with something else? And the reason is that now I go to the very old work, well, what is very old? It's 10 years ago, of Reed and Green. And then they were talking about topological aspects of the so-called Bx plus Ipy state in 2D. Yes? Then, what happens with this state? This is the state where the Cooper pairs have orbital angular momentum 1. Yes? What happens is that if I create vortices in such a system, there are zero energy modes, Majorana modes, on the lattice core. Yes? And then the number of zero energy states exponentially grows with the number of vortices. They are exchanging these zero energy modes. And then what happens is that there is an non-abelian statistic. Exchanging vortices creates a different state. And the ground state has a strongly non-local character, which means that local perturbation does not cause decoherence. And it was generally believed, and even argued, that this is topologically protected state for quantum information. Of course, what is required is also that there is a gap in between this ground state and the first excited state. How dangerous this gap is, it's a different question. People are now arguing that maybe it's not that dangerous, and they give arguments on that, and they do some calculations for the gap. But this is good. So that's what the idea was. Originally, this has been discussed by Grigory Volovik in the context of liquid helium-3. Everything that Volovik has done nicely was in the context of liquid helium-3. Yes, even analog with the universe and so on. And then Reed and Green, they really wrote a very nice paper, which has not been published in Phys Letters and Nature Physics or whatever, just nice physical review paper, yes, but very good paper. And then this was the reason to pay attention to these P-wave states which can be created with outer-core fermionic. And yes?
I just want to ask you, did Volovic know about the Majorana character?
He knew about that. That's what he says.
No?
Well, what means no? He didn't write about that. Yes, but what he said is that in the case of P-wave, there is a quantum transition. This is what he said, and this is a big difference from the case of S-wave, because in the S-wave case, when you move from BCS to molecules, it's generally believed that this is a crossover without readers. In the case of P-wave, there is a quantum transition. Roughly speaking, a chemical potential zero, because here the other parameter is anisotropic, yes, and here it's isotropic. It's just a molecule. Yes, and P-wave means that the orbital angular momentum of the molecule is 1, but it doesn't matter. Yes.
Jura, so this TC is for 3D.
No. Oh, Masahito, I apologized already. I said that here this is for 2D. You know what is usually standing in the VCS exponent? Excuse me, please. I had to correct it. It's exponent minus, 2 pi divided by, or unit, it doesn't matter, f over kf, nu over kf, where this is the density of states at the Fermi surface. And this is the scattering amplitude, yes, modulus. The scattering amplitude for P-wave, I think it's K Fermi squared, and nu is K Fermi in 3D, so it's K Fermi cubed, yes? And, but in 2D, and in a later stage, I will be talking about 2D. The scattering amplitude is also K Fermi squared, but the density of states is constant, so it's K Fermi squared. Okay. And then, you know, all this became very unfortunate, especially for people like Gurari and Radzikowski, who wrote a very nice review article, very nice article has been written by them, how to make these P-wave resonantly interacting system, why it is interesting, how to solve a problem with the narrow resonance and so on. They did a very nice work, but you know, in France we say c'est la vie. Why are you laughing? C'est la vie is a very well-known expression. Yes. But this work has not been done needlessly. They have made a very useful work. Why? Because now we have a new life. And this new life is related to the fact that we now have the creation of outer clouds of polar molecules. So what is polar molecule? Polar molecule is molecule or heteronuclear molecule. Did you ever hear this term? Polar molecule, heteronuclear molecule. If you look in Landau-Lifshitz, volume number 3, usually people from condensed matter and high energy physics, they did not read a chapter regarding these group symmetries for molecules and diatomic and polyatomic molecules. They said, it's okay. Then I had to teach them. This is how Jakub Smorodinsky was teaching me when I was a young guy, that if you read Landau-Lifshitz, please read everything. Yes. And it does not mean that I cannot make mistakes. I can, but to a less extent than other guys. So these are molecules, diatomic molecules, which consist of 2 different atoms. For example, potassium rubidium or lithium cesium. And these molecules have permanent dipole moment. If I forget about the rotation, just consider molecule at rest and calculate the dipole moment, it's non-zero. Yes. And this attracts a large attention. And what has been done recently, that the group at Gila, the group of David Jin and Jun Ye, two groups merged in this project, they created these molecules at densities 10 to 12, 10 to the 13th particles per cubic centimeter, cooled them to 200 nanoK, which is almost quantum degeneracy, just factor 1.5 or factor 2 about the Fermi energy. And you know, and they did the following. First, you have these atoms colliding, yes. Then they form these Feshbach molecules, these weakly bound and collisionally stable molecules that I was talking about. These very nice molecules, but having very little dipole moment. Then, from the point of view of dipole-dipole interaction, these guys are not interesting, but they're long-lived, and what they can do, they can excite them by a laser to the electronically excited state, and then by a different laser to the ground state, ground raw vibrational state, which has a small size, atoms are close to each other, and the dipole moment is significant. And that's what they have done at Gila, and related experiments are done for lithium-cesium molecules at Heidelberg in the group of Matthias Weider. You know, it's very easy to say in words, especially when we are among theorists. Yes, I think that almost everybody in this audience identifies himself as a theorist, isn't it? No, not cool. But so Chris would probably understand that it's very easy to say these words, but it's not at all easy to do this experimentally. Yes, and that's what they have done. They have worked for a few years. This is the achievement. But
also, Shin Inoue at the University of Tokyo have reached this feat for potassium review.
Oh, this I didn't know. Was it very recent?
Very recent, this year. This paper. Yeah, and the difference is that they use a bosonic combination. So potassium 41 rubidium 87.
So they have bosonic molecule.
Bosonic molecule. And another difference is that they create low vibration ground set directly from mode without using pressure.
Okay. I will tell later what the problem is with bosonic molecules. Yes. So thank you for mentioning this. I have to be aware of them. But what they found in Gila, at significant densities, at least at densities larger than 10 to 10, 10 to 11 particles per cubic centimeter, there are so-called outer-cold chemical reactions. For example, two molecules, potassium rubidium plus another potassium rubidium, they collide. They form potassium 2 molecule and rubidium 2 molecule. This is energetically favorable. And this made all chemical physicists very happy. They started to pronounce world outer-cold chemistry, new trends in outer-cold chemistry, and so on. And all people who are doing many-body physics became very unhappy, because a very nice system becomes collisionally unstable. So what has been also done recently, it has been done by Jeremy Hudson, who is a very good and reliable chemical physicist. They have shown that for many, many systems, like potassium rubidium, excuse me please, I think I'm going down, yes, or lithium cesium, this type of reactions, these reactions are present. At the same time, there are pairs of alkaline atoms which form this type of diatomic molecules, but these reactions are absent. They are energetically unfavorable. So therefore, there is a large chance that we just get these molecules which do not undergo this outer-cold chemistry. At the same time, even in this case, there is a way out. How to suppress this instability? I'm not a chemist, at least I hope that I'm not. Yes. And I'm not interested in this outer-cold chemistry. I'm just pronouncing these words for fun. How do I get rid of these reactions? The idea is to induce a strong repulsion between these molecules. What it means is, let us put these molecules in the two-dimensional gyrometer. Let us polarize them by an electric field such that the dipole moment is perpendicular to the plane of their translational motion. Yes? And then, what we do, we get dipoles in the plane. Yes? Dipoles like that, looking in one and the same direction. So such dipoles repel each other, strong intermolecular repulsion. I should only polarize them nicely by an electric field, then I get a strong intermolecular repulsion. Molecules do not approach each other at short intermolecular distances where this reaction occurs, and then I'm done. This is just the experiment that Jun Ye and David Jin are doing right now. Yes. And then, what is expected then is that one can nicely do evaporative cooling for such a system, reach very low temperatures, then expand and decrease the density. And then one can do a variety of things. The rate of this process becomes very low because these are identical fermions if they are in one and the same Hilbert state. Therefore, the inelastic rate is proportional to the Fermi momentum in the square. Momentum in the square in the degenerate regime, Fermi momentum in the square, which means density in the power of 2/3. And if I am in 2D, this is just density. Then it means that I can do very many other things, yes, with this dilute system and forget about this chemical reaction. Yes. That's what the idea was. And then I will tell you, if Yegor will allow me, and if you will allow me, I will tell you a couple of ideas which people came up with. Yes. There are many more.
How 2D should the system be?
Sorry?
How 2D should the system be?
You know, the confinement length in this direction should be much smaller than the characteristic dipole-dipole distance. The characteristic dipole-dipole distance is md squared divided by h bar squared. This is the distance at which particles efficiently interact as dipoles. Therefore, the dipole-dipole distance depends on the dipole mole. So the larger is the dipole mole, and the easier is the situation. David Jin has a problem with that. For example, in their case, the suppression is only expected for fermionic particles. I checked that. Where this k in the Fermi square is present. If David Jin were taking bosonic molecules, then they are not sufficiently 2D. Yes, they have to confine, because in their case, the confinement length in this direction is of the order of the dipole-dipole length, the characteristic radius of interaction. That's what it is. And okay. Now, most of the ideas related to these dipole systems, they originate from the fact that the dipole-dipole interaction, it's unit divided by R cubed. It's anisotropic. Two dipoles like that repel each other. Two dipoles like that attract each other. Yes. They are mostly related to the long-range character of the dipole-dipole interaction. Let me explain you what this is. Let me first make a small observation. It's already 2:40. I will finish in 5-10 minutes. Is that okay? Yes, but if everybody will leave the audience, then we are there. Now, what happens is that let us make something interesting and return to this Px plus IPy topological. Let us, for example, forget about these chemical reactions. Let us think that the molecules that we are dealing with do not undergo these reactions, or the system is so dilute that these reactions are very slow. Let us put the molecule in a two-dimensional gyro. Yes. So the translational motion is 2D, but the rotation is still 3D. Then let us come up with a microwave or radio frequency field. Who knows what is the difference between microwave and radio frequency? Chris Food definitely knows. Yes. What I learned from Jean Dalibard and from Christoph Salomon is that if the frequency of your electromagnetic field is lower than 1 gigahertz, then it's radio frequency. If it's larger, then it's microwave. That's what they told. Is that correct or not?
That's a reasonable definition. Yeah.
Yes, it's a reasonable definition. But the border is not well defined. Yes. Because, you know, before that, I was guessing what is radio frequency and what is microwave and what is really the difference. It turned out to be trivial. And then, so we come up with this RF electromagnetic field like that. The electric field of my electromagnetic field rotates this way because I come up with sigma plus polarized light. And then this light is almost at resonance with the transition from the ground rotational state of the molecule to the first excited state, which means that it puts the molecule into the plane and rotates it. And it puts all molecules into the plane or almost in the plane and rotates in a classical. In a quantum picture, it means that my eigenstates become dress states, which is a linear superposition of the ground state, J equals 0, projection 0, and the excited state. Since it's sigma plus polarized, the projection and the excited state is 1, so J1 projection 1, but the 0, 0 minus alpha 1. And here are the notations, the Rabi frequency, the frequency detuning is introduced, and so on. So then, what is the qualitative picture? I put all molecules in the plane and rotate them. I should write the dipole-dipole interaction and average it over the angle phi. This is the angle between the axis of between the molecule connected to the axis. Yes. Unity minus 3 cosine square phi. It gives me, oh, what is this?
There's no projector.
Oh, projector problem. I thought it's problem on my transference. Okay. It gives me an attractive unit divided by R cubed tail. So the optically induced potential looks like that. There is an attractive unit divided by R cubed tail, there is a potential well, and then there is a repulsive well. And of course, if we do theoretical physics, here it's quite simple. What we have to do, we have to write down the Hamiltonian, diagonalize the matrix, and so on, and that's what we have certainly done. This is easy. Now, let me remember that there is this attractive minus unit divided by R cubed. Then what I do, I say that I have molecules or particles which undergo attractive interaction at large distance, minus unit divided by R. They undergo p-wave scattering because they are particles in one and the same quantum state. But then what I do, I write down the Hamiltonian, which contains kinetic energy term. Excuse me, here delta is the Laplacian, and this delta is the order. Excuse me. It's 2D. Do not blame me very strongly. In 2D, it is as simple only at 0 temperature. At a finite temperature in 2D, I have an algebraic order, yes, and the commonly defined order parameter does not exist. I have to do some kind of density and phase representation and so on, but let me skip that. In the BCS regime, I can always separate, I can always divide system into blocks with a size smaller than the coherence length. Then it's okay. Now I have a gap equation, yes, for the order parameter, which includes this effective interaction, its Fourier component, and multiplied order parameter as a function of k prime, and here is hyperbolic tangent excitation energy divided by temperature. And the excitation energy is a usual Dirac formula. It's square root of this guy plus the modulus delta into square. And then what I get when I do nicely, I transfer myself from the Fourier component of the interaction potential to the offshore scattering amplitude and do all these things which I described in length. Sorry, because of work of Zaloshinsky, yes. And then what I obtain is that the transition temperature is, roughly speaking, Fermi energy multiplied exponent in the power of -1 divided by k Fermi R star. And what this R star is, this is the so-called dipole-dipole length. If there is a dipole-dipole interaction, d squared divided by r cubed minus or plus, there is a length md squared divided by h bar squared. At distances larger than that, the relative motion of particles is already free. It feels the dipole-dipole potential at this distance, r star or small. Therefore, this is the distance which characterizes the dipole-dipole strength. Yes, and therefore it's coming. Yes, and the ground state is Px plus Ipy state. That's why I was telling you about Px plus Ipy, which means that the order parameter is exponent in the power of I phi. Does it surprise you that here I have unity divided by K Fermi for the 2D case? No one asked a question, which means that either I said it very unclearly. Because what we usually do, in the two-dimensional case, my scattering amplitude is unity divided by logarithm of, let's say, certain characteristic atomic energy divided by energy, which is Fermi energy. And therefore, the transition temperature is exponent to the power minus logarithm or its square root of this atomic energy and the Fermi. Here, I just write you formula, which is typical for the S wave in 3D. Why? It's very easy to understand, and let us just recall what is happening in the case of atomic fermions. In the case of atomic fermions, where you really have a short-range interacting potential, which decays at large distances as unity divided by R cubed. Yes? What we have is the situation where the scattering and effective interaction and scattering amplitude are proportional to K squared. In the exponent, in the BCS exponent, I have -1 effective interaction or scattering amplitude multiplied the density of states. In 2D, the density of states is momentum independent. K dk, dk squared, dk. And then, and this guy is K squared, therefore Tc is proportional to exponent to the power -1 divided by K Fermi B in the square. It's vanishingly low. This is the case for short-range interacting atoms. Yes. Now, we have a long-range unity divided by R cubed tail. And this is very, very important. Why? Because in this case, there is the so-called anomalous scattering. This is the scattering which comes from distances of the order of de Broglie wavelength of particles. Yes. What is the P-wave scattering? Let us just write down contribution at large distance. This will be G1, well, its exponent ik r minus ik prime r d over r dr 2 pi. Yes. R d over r is unit divided by r squared, is dipole moment here. And then this guy will be G1 kr in the square, because k modulus of k prime is equal to k for the potential length. And then dr. Let me make kr a new variable, and then I get k squared k. This contribution is proportional to k. It comes from distances of the order of the particle, the Broglie wave. It's called anomalous scattering. And this anomalous scattering does not occur for short-range interacting potential. If the potential is unit divided by R6, the contribution of anomalous scattering is k in the power either 3 or 4, it can be omitted. But in this case, it's important. Therefore, this V effective or scattering amplitude is proportional to k, kr star actually, and then Tc in the power minus unit divided by the density of states, and effective interaction scattering amplitude is exponent in the power -1 divided by k. Well, it's not 1, there is a numerical correction. Therefore, accidentally, we get the result which more or less looks like the S-wave scattering in 3D. And this is important because, you know, here you have minus unity divided by k Fermi B in the square, vanishingly low. Then I made a very little trick. I said, I do not want short-range interacting atoms anymore. I wish long-range interacting polar molecules, where the interaction potential behaves itself as unit divided by RQ. And then this guy is replaced by this guy, which means that in the BCS regime, where the system is collisionally stable and doesn't undergo this horrible collisional relaxation, but which makes molecular physicists happy, yes. Then, in this BCS regime where the system is stable, the transition temperature is not vanishing below. Because if I calculate this guy, the ratio of Tc to the Fermi energy, and here I roughly speaking have Fermi energy, is something like from 0.01 to 0.05, 0.03. The Fermi energy can be made 100 nanokelvin, 300 nanokelvin. Therefore, I have transition temperature, let's say from 1 to 10 nanokelvin, which is okay. Now, but this is not the full story, because I can be said by many other people that what you do is extremely simple. It's physically very interesting, but can you do the problem nicely and theoretically? And the answer is, I think I can. Yes. What I then do, then let us do better than simple BCS. Reveal the role of short-range physics, because what happened in my case is that I get here only the distance r star coming from the table. And what is going on here at short distance, I did not describe. Let us do the following. Let us write a renormalized gap equation. It's written in this way. Usually people write here the so-called vertex function. But it's I can select this vertex function such that it coincides with the off-shell scattering amplitude. And there are these two terms, this tangent and then this term. Yes. It's always very nice to deal with the renormalized gap equation, because then if you know the off-shell scattering amplitude, then you just have a nice solution. And this just shows how, well, how numerical calculation the order parameter behaves itself at small moment. It grows, reaches maximum, then stays constant. At larger k, it will go down. So then, what we can do, we can say, okay, let us now try to find the scattering amplitude and then solve the problem. It turns out that it's not that simple. You know that because we have to find the scattering amplitude at finite momentum. Yes, we are not it's 2D. We are not satisfied with the case k equals 0. For power law potentials, there was a very, very nice work written by Vanier, actually in 1952 or 53 or 54, do not exactly remember, where he made an exact solution at a finite energy for unity divided by R4. It's a very nice work. Unfortunately, the result is expressed only in terms of cos-Mathieu functions. One can do very little with them. And second, this has only been done for this type of potential. For unity divided by R cube, it's not done. Mathematical physicists were actively working on that, and there are people representing solutions in terms of series of Bessel functions and so on. But when you ask them, can you extract something out of this solution? And the answer is yes, we can extract very interesting mathematical relations. But then, I'm usually, in the Landau school, they teach us to ask sharp questions. And the sharp question is, can you write down the scattering amplitude at small momentum, analytical expression? No answer. Okay. Therefore, we have to solve this problem ourselves for low momentum, and then it's absolutely non-trivial, because you have contribution of short distances and you have contribution of large distances. Then what we do, we divide the range of distances into two parts. Distances smaller than a certain distance of R0 and larger than R0. This distance R0 is chosen such that it's much larger than the characteristic dipole-dipole distance. So the relative motion here is free, but we still have kr0 much smaller than 1. And then what we do here, we match the exact zero energy solution here with the free motion solution here with the proper phase. Yes? And then For r smaller than r0, the contribution to the scattering amplitude is k squared multiplied logarithm k, and under logarithm I have something which depends on this r0. And the contribution from here considers the interaction as perturbation. It has a term k, and also k squared multiplied logarithm k. And here the guy also depends on this factor. But when I make a summation of the two results, the dependence on this artificially selected R0 disappears, drops out. I get a very nice scattering amplitude, and for simplicity I wrote here the result for the on-shell amplitude, and that because we obtained it for the off-shell. Yes. So what we actually have, we have this k squared term, which is k squared logarithm k r star and multiplied q, and this q is a certain dimensionless parameter which depends on short-range physics. And then here I wrote the off-shell contribution for this k part through a geometrical part. Then, what you do, you substitute this amplitude, actually this one, into the BCS exponent, amplitude, density of states. You have k and k squared term here. And if you make a proper expansion, you see that you get this guy, which I was writing previously, plus logarithmic term. Logarithm in the exponent means power. So this changes the power of the Fermi energy in front of the exponent. Okay, but you know, in this case of P-wave scattering, what we decided to do, if we are interested in numerical coefficients, we have to recall that the BCS approach, even if I solve the gap equation nicely, does not give a correct answer, because it does not include the so-called second-order Gortkov-Milik-Bar-Khudarov processes. Very nice work of Gortkov from 1960-something, 61 or 63. Cooper pair is in the incoming channel. Then one of the atoms of the Cooper pair pushes a fermionic atom out of the Fermi sphere, then interacts with the his Cooper pair partner, puts it in the empty place in the Fermi sphere, and forms a Cooper pair with the guy which was pushed out, one of the diagrams. And then I get an extra term, this delta V. It's sometimes in condensed matter, it's called polarization of the medium and so on, explained in different language. Yes, I explain it in a way I like. So we include this guy. What it does, it changes the numerical coefficient in front of the exponent. And that's what these Gortkov-Milik-Bar-Khudarov second-order processes usually do. They do the same for the S-wave in 3D as Gortkov originally did. And then we obtain here Tc is Fermi energy in the power 0, 3 multiplied this exponent, then sort of atomic energy multiplied in the power 0.7, and the coefficient kappa coming from this guy, which depends on the short-range physics and can be varied within 2 orders of magnitude. When we approach resonance, this guy grows. You know, it's quite peculiar that you have to, if you do a computer calculation of the scattering amplitude, you fail. Why? Because the scattering amplitude contains this logarithmic term, and this coefficient u is in the argument of the logarithm. You can hardly resolve it. But then, in a later stage, it will be in the exponent, this logarithm, and this u, it comes out of here. It's sitting here in kappa. Therefore, in order to get a correct answer, this is one of the cases where you have to do analytics. Yes. Now, let me show you that I was not lying very strongly, because what we have done, we selected the state which is not the ground state, which is not the lowest energy. There is a state which has lower energy. Therefore, there are transitions to the state. The system is still unstable. But we are in the BCS regime, yes? And therefore, the inelastic process is accompanied by a large momentum transfer. The inelastic rate for fermions is proportional to K Fermi R star in the square, multiplied this coefficient, which depends on this large momentum transfer, exactly 10 to minus 3, 10 to minus 4. And these are the numbers, yes, which means that the realistic density is 10 to 8, and the characteristic lifetime will be a couple of seconds. And And then we considered these molecules and put dipole moment 3.5 debye as it should be for this molecule. Then the Fermi energy is 120 nano-K, and then we end up with around 10 nano-K, 5 nano-K superfluid transition, which looks realistic. You know, what I actually have done is looks like a small trick. For atoms, we know that the BCS regime is not interesting because the interaction is short range and the transition temperature is vanishing below. But the system is collisionally stable. Here, I introduce a little bit of collisional instability, but small one. At the same time, I introduce this long-range unit divided by acute tail. Yes? And then, which makes the BCS transition temperature much, much higher. Long-range attractive tails are very useful for obtaining a high transition temperature in the weakly interacting region. And this is one of the main ideas, and therefore, this PX plus IPY topological state looks realistic with dipole particles. What I have, if you were not requiring a review, I could tell you about bilayered systems, but I think that if there will be volunteers, I will tell you about very interesting work which has been put on the web. It appeared this morning, yes, where I made very nice calculations together with a couple of other guys on the S wave and so on. And so the message is the following, that remarkable results have been reached for atomic Fermi gases, and even more remarkable results are expected from the studies of outer polar molecules. We are expected to have wide avenues to make new quantum states, and one of the examples is this PX plus IPY topological state for identical fermions. I was going to say a few words about BCS-BEC crossover in bilayer systems of fermionic dipole systems. Chris, bilayered or bilayer systems? Doesn't matter?
Probably doesn't matter too much.
Okay. I had a long quarrel with my co-author on that subject. None of us is a native speaker. Yes. And Chris told me that maybe bilayer is somewhat better. Yes.
Yes,
So,
Chris.
huh?
Yeah, you changed. Both of us are called Chris.
Yes, Chris Foot told me. Yes. Yes, sorry, you are both Chris, you are both real native speakers. Yes. Okay, doesn't matter. So there are very many interesting things which can be found in the case of polar molecules because of the role of the dipole-dipole interaction. And what I think at the present moment, I started maybe slightly later because of the computer problem, but I'm already speaking. I started 1:50, and now it's 3:05. I'm talking 1 hour 15, even 1 hour 17 or 18 minutes. I think it's enough. Thank you for
it. I did my undergraduate at the IOF Institute. We had the following convention for seminars. The speaker was told that the seminar starts at 5 p.m. with a sharp cutoff. The sharp cutoff is set when the last subway train leaves.
You know,
so I'm trying to implement it here.
You know, when I was in Amsterdam, it was half a year after Steve Chu got the Nobel Prize. And then he was invited to Amsterdam to give a colloquium. It was at the University of Amsterdam. I was at Composition Amherst at the time, but we are with the university. And then he was giving a very, very long colloquium, which was lasting 2.5 or almost 3 hours, telling very nice stories about Sweden, Swedish royal family, how he was getting the Nobel Prize, and so on and so forth. And then everybody was listening to him, although in the end everybody got tired. And then, but he was showing very nice photographs, so everybody said like that. Then, a few months later, Jerry Gabrielson from Harvard came, also to give a colloquium. And then he said, I heard that there was Chief Chu giving a 3-hour colloquium here. I'm going to prove that I can talk as long as Steve can. But he was not allowed to talk 3 hours. He was he did not have the Nobel Prize.
No questions? Question. So this in this dipolar systems, it's mimicking spinless fermions, right? So far as
yes,
can you have spinful fermions?
yes. The system that I was considering, this Px plus IPy state, is for spinless fermions.
So can you have systems which look like spinful fermions? Spin 3-3?
Yes, of course, and this is what I'm having in my transparencies. Let's say two dipoles in different internal states. This mimics spin 1/2 systems, 3-component systems or whatever. Yes. In fact, when they first created these dipole molecules at GILA, they had 36 internal states. Yes, which is a lot. Now they can make 1, 2, 3 states or whatever. So yes, there are ideas what interesting one can get with 2-component dipole systems. Yes, there are such ideas. People are working on it.
This may be a very dumb question, but I mean, your conclusion slide, you mentioned the BCS-BC crossover for bilayer dipolar system, but I mean, is this crossover? Does this crossover require bilayer system, or can you have it for like a identical dipolar molecule system as well?
Well, you know, people were studying in literature just BCS-BC crossover in the 2D case. Mohidra and Deria did that in the context of secret activity quite some time ago. The thing is that what do we call BCS-BC crossover? We call the system where on one side of the resonance or whatever, the system is in the BCS regime, then it goes through strong interactions and reaches the regime of molecules, bound pairs. I do not know whether one can do something for dipolar particles in the gas phase without violation. Because there, what I need weakly bound molecules. And then I'm not sure that I can nicely create weakly bound molecules in the 3D case or whatever like that. Yes? I'm not sure. I didn't work on that. You know, with bilayered systems, it's quite interesting. Very interesting physical problem. Think of it. Imagine that you have 2 layers, yes, and 2 layers like that. Yes, here is a dipole and here is a dipole. Yes, and then the question is, can these dipoles form a bound state with each other? Both dipoles are perpendicular to the plane. Do they form a bound state with each other or not? And people working on excitons made a mistake saying that there is a threshold for forming a bound state. They did not read a very nice paper of a mathematical physicist, Barry Simon, from 1974 or 73, where he gave a rigorous proof that for bilayered system of dipoles, 2 dipoles like that, always form a bound state. Always, whatever the distance is between these layers, whatever the dipole moment. And it's a very peculiar problem because there is a very well-known result in literature that if in 2D V over R, R dr, is smaller than 0, and the potential is finite at the origin, there is always exponentially small bound state, Landau result. But in this system of dipoles, this is exactly 0. If I write down the dipole-dipole interaction between these guys, this integral is exactly 0, and the ordinary method does not apply. And you have to do the work yourself in order to show that, in order to calculate the energy of the bound state. And Barry Simon did for you the statement long time ago, the proof that it always exists. Now you have to calculate. And then So in bilayered systems, you always have this bound state, which means that if the bound state is extremely shallow, then fermions like that attract each other in the BCS regime. If it becomes tighter, the size of the bound state in the in-plane direction is smaller, then these are nice composite bosons. And in the gas phase, I do not really know whether one can invent a very nice molecular state. At least I didn't think of it. Yes. Thank you for asking this question. Maybe it will stimulate me to think a little bit.
No questions? Yes, that's it.
Yeah, it's an interesting question. I think it does refer to very much.
Thank you very much for your talk.
Thank you for listening to me. You took quite some time. Thank you for patience.
Many layers.
I would probably reformulate and put the word bilayer somewhere else.
Turn around and ask me that in the office.
When you did this,
Then you shall see
one
taking a
with a K, and then you have this ECS, PC, which is, you change that now, right? And now,
So
how
the
does
person
this show up in
in
your schedule
Tokyo
and
then,
details?
is that working with your group?
Yeah.
You have a bigger group
The
under
scattering amplitude should contain
So
logarithm.
but this is not degenerate. This is
Yeah, right. Not this
Also,
one.
not in a starting.
They start from mod.
The thing is that usually
Yeah.
for short range
For potassium 41.
41.
zero.
So how do they affect the CP2?
That's ionization.
Is it their or your intention to sort of carry on and do that, or you know the degeneracy?
Since it's a body, so we have to push that system and then otherwise it maybe collapses. So the next step is to load the system. Now it's about
Why did you choose 41?
Which reason is July is 40. Another reason is actually as a mixture in the Genesis system, BC, both are BC, then there's a visual response between you and 41 to 87. Then maybe we thought that this is more interesting.
you wrote that in now the scattering amplitude is actually going faster.
Just one system. Then how the other system follows.
So at higher density,
Depending
then
on the
going on
inter-BC.
faster than
Initially, 5 years ago, we are not pretty much sure whether we could reach
You have
any
here.
vibration over the frequency. So it's a hedge. It's a hedge. Yes.
Therefore, this term is much.
Because that's one thing I'm not quite certain of yet, and maybe Emmanuel Bloch would
This
talk about
term
it.
is much.
If you put two species in an
It
optical
only
lattice,
becomes
then if
important
you want to
because
make
it shows
molecules,
up
then
in
the ideal
form.
thing would obviously be that each state
If I were
has
just
a
calculating the
multi-insulated type
midfield
transition.
difference, I could
So you've got
forget.
one rubidium and one potassium in
At
each
low,
plate.
yes. Yes.
But they affect
when I
each
put
other.
this guy in the exposed,
But can you tune the scattering length?
Okay, I see.
Interspecies scattering length to zero
Just
so
because
that
it
they
is
just
in the
pass through
exposed.
each
Yes,
other?
yes.
this is the idea of
There's a nice
Yeah, okay,
at low model field.
So yeah, so the other term just give you the ordinary exponent.
yes.
E to the
And also
minus
your
1
question,
k
you asked Jura about how to deal.
Okay.
Perhaps you know the answer anyway. I don't know whether you want to.
Well,
But I think there is a paper out there on that.
Thank you very much.
From
Welcome.
Julien and the
So you are leaving tomorrow,
showing,
today?
you know,
No, I'm not leaving today.
because in their case
and
they
I'm
do
not
have
leaving
these reactive
tomorrow.
collisions
I'm
and you know,
dealing
how
with
tight
the
confinement
confinement.
they need.
Tomorrow we have an
Suppress
idea
them.
to go to the Nordic Museum. It looks like a very interesting place.
I don't
I
think
have
that's
been to this Vasa Museum. We have been to the sculptures so far.
bipolar
We have been
repulsion
to the
makes
historical
the system
museum. I like to go to
metastable.
historical museum.
But if there's
So,
a
and
direct
then we decided
new
to
Korean
go
channel
to
that's
this,
low
Nordic Museum. And
low
there is also
chemical channel,
sort of
then
art
maybe it
museum
could
somewhere
easily
in the center or something.
like this and
Yeah,
you
depends on what
go
order
there.
you're interested in. Is the National
So,
Gallery, you want Sweden
Usually the
State,
calculation
Ford
for
Museum, but
this metastability
they have a nice
is based
selection,
on
but
some
usually less specific.
but
And there are
whether this
small, nice museum, but if you want to stay in
That's
the
also-
city
that's
center,
also-
presumably
we
you
rely on more microscope.
National Gallery.
So that was your
Yeah,
point.
that's what I thought.
Already got, so.
We have a day tomorrow.
But I mean, that doesn't apply. Does that apply equally? Because I mean, there are species like you mentioned, Jeremy Hudson, as rubidium, potassium is not reactive fusions, but like rubidium, cesium, and I think actually quite a lot of other ones don't have these reactive collisions.
Yeah,
I'm
yeah.
not sure whether there are then other collision
Yes.
processes.
You know, just walk around, you've been through the old town.
I think
Yes.
this is the region
Actually,
where
I visited a
region.
large part.
yeah, and maybe there might be
Stockholm
some
15 years ago. 15
nice
years
nice
ago, I
conditions.
was a guest professor.
yeah, but
I was in Amsterdam, but once in a while
maybe the
I
experimental
became a
part.
guest professor
Yeah.
at the
Because
University.
we were probably going to do potassium, rubidium
Yeah.
as a starting
What we
point.
decided
I think
to
we're most
do with my
interested in
wife
doing
and
potassium,
daughter,
cesium.
We decided to take a trip by these ships.
Seems like
Syria
potassium,
Line,
lithium,
the
one system. But anyway.
which
And
go
maybe
between
something
Finland
that cesium,
and
cesium lithium.
Well, you are right.
Yeah, it's got a very, it's got the highest
They are not
dipole,
only
obviously.
drinking,
but
they
it's
are
extreme
playing
cases.
because
I don't know what that is other
The
problem.
Finnish guy who was
Well,
the
I
captain
think
us. And the
I
first
heard
evening,
that they
he got very drunk.
this-
He lost
this
all his
cesium
money in the casino and came to me
this
saying, "Give me money
combination
because I
has-
have no money."
has
I
less
told him,
inner
"Now I
support."
should gain."
Ah,
I told
I'm
him
not
that
quite
he
sure
should not
about this,
drink,
but
go to bed. He was not
okay, that's been
convinced.
demonstrated or
not
calculated.
Yeah, I know, they are famous already.
some
Yes.
And you mentioned that at Heidelberg, but that, I mean, the Heidelberg work again, I think that's,
Yes.
you know, that's astronomical.
Yes, but in former times it was terrible.
Oh, well.
But I mean, I think
Earlier.
several groups are setting up cesium
You know,
lithium experiments.
I
Chin,
was
Chin,
in the
and
city,
also,
which
I
city
think
it was?
possibly in the
that
UK.
came called? I think it was the city of St. Petersburg in
Well, there's
1986.
this
I
Lucia Hackebuller
went
who
to the
worked with,
Netherlands
she
from
worked
Russia
with
in 89,
Amanda
so
Bloch.
in 86 I was still
Where-
in
where is
lockdown.
I think she's,
And
well,
we had
I'm not
a
sure
conference.
apparently, I think it's a bit sort of rumor.
In
I
St.
think she's got a
Petersburg,
job in
organized by
Norway.
people from the
So they said that that was,
Institute.
I guess you see, you know, people
And the
now have a
location
chance of
of the
hindsight and
conference
they
was
can,
at the border of
heard
St.
these
Petersburg.
talks and
There was a very
discussions
nice
about that being
international
favourable
with a nice garden.
on setting up from scratch now that no one can consider.
It was enormous. Then, we came here in the morning, and
think that chemical
the first picture that we saw,
chemical reaction
right,
it's so
not
easy.
far from the reception,
Yeah.
was a
Yeah,
Finnish
I mean,
tourist,
for example,
8 o'clock in the morning,
our next
sitting on the
indication
table,
is that after loading
not on the chair, but on the table, and drinking vodka right from the bottle, without
we are
getting
curious
glass.
about whether
Yes.
what
Then,
the yields
okay,
rate, whether we start from this
and,
configuration
then,
or this
and there
configuration.
was a guy among
Can
the
we
group of
control
Finnish tourists,
Inner question
which
by
who we really called
external.
our fourth friend. Because the guy was either sitting at the table, talking
Yeah,
to his people,
chemical
drinking and
reaction
eating,
is
or
but I mean, I think
he was just
things to see.
walking like that to his room. Never on 2 feet.
Can I ask?
Yes, you can.
You know, and the discussion yesterday.
Yes.
So, it's these pictures that they show.
Yes.
So, what is the, you know, certainly, if say that you had an ideal gas, so, or completely non-interacting, so it would be infinite viscosity formally, then it would just spread in all directions. Now, how much, from just looking at these pictures, if you look at the pictures that were published in Science, I think, these more complicated combinations in 2005, you see that the time evolution of this is really like this. Finally it becomes like that. At least when you look at the pictures, you cannot really see any expansion in that direction.
This is true.
Yeah.
This is true. Yeah. It's because it's in the hydrodynamic regime.
Yeah, but also low viscosity.
Yes.
Because I mean, hydrodynamics in principle you can have for any. But the question is really, how much does this picture tell me? I mean, because as you pointed out, of course, both condensate would give me, for different reasons, qualitatively same looking things. The physics would be completely different, because then you would say that you would just, you know, say some initial velocity distribution of a free gas rather than seeing a push in a fluid.
Let me tell you the following. I just repeat what Lev Pitayevsky said. We discussed it long time ago. And we arrived at this conclusion that as long as the system is described by hydrodynamic equations, let's say earlier equation and the continuity equation, then your expansion will be, as you showed here, anisotropic. And then it condensates. They obey the Gross-Pitayevsky equation. But if I turn to the density phase representation, introduce density and the gradient of phase velocity, then what I obtain out of the Gross-Pitayevsky equation are two equations: the continuity equation and the Euler equation.
And the continuity and
Euler.
Euler, yeah.
Do I pronounce wrongly?
I don't know.
How do you pronounce?
I say Euler. I have no idea.
I say Euler. Okay.
You better check with a native speaker, whatever native is.
Are you a native speaker or not?
Yes, but Euler was French, was it?
No, I think he was not French.
Was he German?
Yes.
Okay. I'll ask my German friends.
Yes, I think he was German. And then, in the case of a thermal gas in the hydrodynamic regime, the hydrodynamic regime means that the mean free path of a particle is much smaller than the size of the system. This is the only thing.
Or size of the typical flow, I guess. I mean, typical flow gradients.
The thing is that what happens in real life is that if it's an ordinary hydrodynamic gas, then in the course of expansion, you leave the hydrodynamic regime. You first are hydrodynamic, but in a later stage you become homogeneous. But it doesn't matter. The anisotropy of the expansion is conserved in the velocity. Because if you are already in the regime of free expansion, then the aspect ratio